one Form Symmetry and its application.
Thank you so much. Whoa, it's really loud. There's like a huge echo. Okay, I'm very happy to have this opportunity. It's just an introduction to one Form Symmetry. There will be not very many new results that I'm going to present. I'm just obliging to Qumran's request to explain the subject to you. So it will be not extremely rigorous or mathematically heavy explanation. It'll just be intuitive, and I'll try to make contact with the main subject of this workshop. And so there will be contact with many talks that we heard over the last few weeks, and also with Hiroshi's talk on the beach last week. So what is an ordinary? Oh, this is not movable. So what is an ordinary symmetry in quantum field theory? An ordinary symmetry, which I will call zero form symmetry, is defined as follows. So it's defined by a topological surface. So that definition turns out to be convenient and generalizable to what we will come to call one form symmetry. Also, if there are any questions, please stop me. So it's a topological codimension 1 surface. Codimension 1 surface. So what it means is that we have a certain, unfortunately this is not movable, so I'll move here. So we have a certain surface sigma, whose dimension is d minus 1. Yeah. So eventually I'll hide these blackboards. So an ordinary symmetry is defined as follows. We associate topological operators that act on the Hilbert space, and we'll see. And they're associated to some codimension 1 surfaces, and the operator is denoted in this fashion. So you're given a d minus 1 dimensional surface, and then there is an operator that is a function of that surface. And the idea is that this operator is a topological operator. So it does not depend on the exact shape of sigma. What it cares about mostly is just the location of the sigma with respect to other local operators. So if there is a point inside that surface, since it's codimension 1, it makes sense to say whether a point is inside or outside. You might get one answer. And if the point is outside, you might get a different answer. But it won't matter if you move the surface like that. It only matters if it crosses a point. So this is how ordinary symmetries are defined, and we write it in an equation in the following fashion. So given a group element G, so G is a group element, so we have some operator that's associated to a group element, and it's supported on this d minus 1 dimensional surface. And then there might be a local operator inside. And you can compare what happens if it's inside versus outside. And we write it in the following fashion. So that's how we write it in this way.
And these are space-time.
Yeah, this space-time. So I'm Euclidean at the moment. And then there is some group element here, G, that acts on O. Okay, so operators transform in some local. O is a local operator, so that's a more familiar object. O is the local operator, and these topological surfaces, when they wrap this operator, you pick up a transformation, a linear transformation of the group G. So that's how you compare this situation with this situation where it's outside.
And the operator acts on which Hilbert space?
So this is Euclidean. This is a Euclidean formulation. You could also write it. So in Euclidean space, we just take some codimension 1 surface, and we try to shrink it around the point, and we get G of O.
So this is independent of how you chose your Hilbert space.
Right. This is completely Euclidean. Now, if you think about it, Euclidean-wise, you can put the operators at some time, and then you integrate over some time just slightly before, and you compare with what happens when you integrate over some time just slightly after, and you pick up a linear transformation G. So this is like a commutator. So it becomes like a commutator. It can be interpreted as a commutator in Minkowski's signature.
Right. But in Euclidean space, you can also choose a Hilbert space. That does not have
right.
I was asking whether your Hilbert space is based on sigma or not.
No. In Euclid, it's just like any sigma that encircles this point.
Your Hilbert space is over there.
This is independent of the Hilbert space. This is in statistical mechanics. You have a topological surface, you wrap a point, you get the G.
To use an operator, operates on what?
Right. So you should think about it as an operator if you want to think about it as in Hilbert space, like in Minkowski signature, for instance.
We can think of Hilbert space. That's not
Right. I shouldn't have said an operator. It's an operation. You could, whatever. In Euclidean signature, you could just think about it as some action on the lattice, for example. You can just define some defect on the lattice. You can call it U. You prove that that defect is topological, and you show that when there is an operator, yes, it's some insertion in the path integral, and when there is a point inside that defect, you pick up some transformation G. Yeah.
So, how do I distinguish this? How do I know that this is a symmetry?
Topological. This is the key word. So, what distinguishes generic codimension 1 operators from symmetries is the notion of being topological. That's one. And the second issue is that it has to be associated with a group element. And in particular, it has to be invertible. Because, as you see, since I assume that this is associated to group elements G, we are assuming implicitly that these operators are invertible. They don't have to be invertible. There could be perhaps somewhat esoteric examples where they're not invertible.
But everything here is a linear.
Yes. Well, linearity and associativity follow, but invertibility does not follow from the axioms. So you have to assume that it's associated to a group. That's the most familiar construction of topological operators, is that they're associated to a group of symmetries. Okay. In particular, we have the following relation, that UG prime is UG prime, where this guy is inside that guy. So we're imagining a picture like that. So this is G prime, this is G, this is an O, and this is, and this is just one guy, GG prime. There is O. So we have the usual multiplication rule in the group. Okay. In this language, one-form symmetries can be defined rather easily. So what is a one-form symmetry? So these are ordinary symmetries. It's just like any standard symmetry in QFT would be of that sort. And by the way, this is also easy to define for discrete symmetries. So this definition is easily interpreted also for discrete symmetries. That's the advantage of that definition. Now, one-form symmetries in this language are just topological codimension 2 operators. Sorry, topological codimension 2 operators. Well, operators in the, again, with these quotation marks, that it's not interpreted right away as a Hilbert space. It's some defect in the path integral, if you think about it as a Euclidean object. So we have U of sigma d minus 2 now. So these objects are far less familiar, and I don't think any standard book in QFT would cover these objects. But they've turned out to be useful for very many applications in the last 2 or 3 years. So that's what I'm going to explain today. Yeah?
So in 4 dimensions, the usual one would be associated with charges, and these would be associated with fluxes.
I'll give lots of examples soon. Yeah. So let me just cover a few applications of those, and then we'll derive a little bit of the theory of those guys. So first of all, they're more or less inevitable when you study bosonization in higher dimension. Bosonization in higher dimensions more or less implies almost by definition the existence of such objects. It turned out to be very important to understand those objects when you want to study Yang-Mills theory at finite temperature, and even at 0 temperature, in fact. And also it turned out that these objects exist rather naturally in some constructions of hydrodynamics, and there were many other applications in mathematics. Also for phases of matter, phases of many gauge theories, or phases of many QFTs, topological phases of QFTs, and so on. So there has been a lot of work on those objects in recent years. I won't be able to even start listing all the authors who have contributed to that subject. But I'll try to give you a quick introduction to how these things arise, what is the connection to this workshop. So these objects are not going to wrap local operators, because just think about 3 dimensions. D equals 3 is the easiest to visualize. So then this is an operator that's topological and it's supported on a line. So it cannot wrap in any sensible way a point. So what these objects wrap are lines in any dimension. So they wrap lines, not points. In 3 dimensions, it's easy to visualize. So the algebra, so if we have a line, let's call the line W. O was the local operator, W is a line, and this will be our U. So we'll write a similar equation to this one. So the defining equation is very similar, except that instead of acting on local operators, we act on lines. So we have some group element G, then we act on a line, and then we get some transformation of the line, as before, and U of G sits outside. And this is under the condition that W is enclosed inside U. So there is a non-trivial linking number between the two if you're in 3 dimensions. Right, but it will be still true that this wraps a line in any dimension. So this always acts on lines. So you cannot pull a line out of this thing. Okay? So one little immediate...
Just since you have raised a 3D version, you can imagine this being knotted with respect to each other, not just simply naked.
Right, right.
Then you could ask what transformation depends on which knotted version it is.
Right, it could be that this guy has a more complicated knot, and
I mean, this line goes around it.
yeah, it could be that it goes around several times.
What is that transformation change?
Well, basically, every time you can imagine the way you would work it out is that you would imagine pinching. Every local pinching buys you a group element G. So you would just pinch it. You would just pinch it until you can separate them completely.
Does G have to be?
Is that fine?
Make sure it's another abelian in some form, or?
So a corollary is that the symmetry G, for which is associated to this construction, it must be abelian.
So just to make sure I understand, if you did Chern-Simons theory, for example.
Yeah, we'll do Chern-Simons theory as an example soon. Yes.
In that case, it's not abelian necessarily.
Well, but there is a subalgebra of abelian anions, which are the U's.
But you could have imagined more general. So this is you're restricting to these guys.
No. I'm just saying that anything that obeys
Oh, you mean there are
the subset of lines in Chern-Simons theory that obey these relations are a subalgebra of the anions, and a abelian subalgebra of the anions, and it exists in almost every Chern-Simons theory that you know.
You can have, you have
So Chern-Simons theories have a lot of one-form symmetries.
In other words, the objects that correspond to different.
They're in representation of the abelian subalgebra. Yeah, I'll do these examples in detail soon. So a corollary is that one-form symmetry must be abelian simply because if you have 2 of those guys, unlike the previous case, there is no notion of who's inside, who is outside, and you can just make it like, you can just squeeze it inside, so it must be abelian. G prime must be the same as G prime G.
So G, in principle, you could imagine that G would depend on where you are on the line.
No, but it's a topological codimension 2 operator. As long as it doesn't pinch with other lines, it doesn't change. The path integral insertion, whatever, doesn't change.
I said on the line, right? It doesn't depend on the point on the line. It's really global on the line. I'm not talking about.
Say again.
I'm just thinking. Okay, no, go.
So is the argument why this must be abelian clear? So this is unlike 0-form symmetries, which can be non-abelian. Is it clear why it's abelian? Okay.
Can we describe non-abelian one-form symmetry?
Well, I don't know how to do that. I don't know. So as I said, my introduction is not rigorous. So you could imagine that there are slight issues with formulas like the one. So there was previously a formula like UG prime is the same as UG prime UG. You remember that formula? That came from taking 2 codimension 1 surfaces And that was GG prime. I confused the one form and the zero form. So that formula came from taking two codimension one surfaces and imagining that you can collapse them to the group element. But there may be issues with this. You can imagine various situations where maybe this is not true. So in systems where there is both a one form symmetry and a zero form symmetry, it might be that when you take codimension one surfaces and you collapse them, there will be a codimension two leftover kind of defect. So it might be that the algebra of zero form transformations does not close on itself, and you spit out one form transformations. This is known as a two group. Okay, and it could also be that this is also only projectively realized. That's another way in which it can fail. So two group, I won't discuss two groups, but two groups arise when the subalgebra of zero form symmetries is not well defined. When you take two codimension one surfaces, you collapse them, and you get some codimension two surface.
So maybe related, maybe not, I'm not sure. I could have imagined a situation where instead of having a d minus two-dimensional object, you have a boundary of a d minus one-dimensional object, which is a d minus two-dimensional object. In other words, you can combine.
Okay, I'll discuss that now. Good question. So Cormoran's question is, how do we think about objects that are boundaries? So codimension two objects that are boundaries of codimension one objects. So this is an interesting question. If this codimension one object,
let it go from the beginning to say that it can be projective. So assume that the ordinary one is projectively realized, right? And then you have the cosine, which will require to have codimension two object for that to satisfy.
Right. That's how we get two groups. So there are many interesting physical systems. So I'm going to describe extremely simple examples where there is zero form symmetry, one form symmetry, and they don't talk to each other. So the two group is trivial. But there are interesting examples where they are interlinked, and the zero form symmetries in fact don't make sense. So this is it's not a sensible subalgebra. So Cormoran is asking what happens when we have a codimension two object that is defined at the boundary of a codimension one object. So what's the right terminology here? So there are two cases here. So if the codimension, if the codimension one object is not topological, it's just like a generic codimension one surface, there is nothing to discuss. So there are two interesting cases where the codimension one object is topological, but non-trivial. So meaning that when we enclose some local operators, we do pick up some phases, or we do pick up some transformations. So this is topological non-trivial, or it can be topological trivial, meaning that it doesn't even see any local operator. And that topological trivial, I also call transparent. So it's completely transparent to local operators. These are two cases that we have to distinguish. If this is the situation, then we can just forget about it. Because even if there are some local operators here, we won't care if it's like this or it's like that. It doesn't matter. In this case, the boundary is a genuine codimension two operator. So the boundary is a codimension. So the boundary becomes a genuine codimension two operator. In the first case, we cannot forget about the surface because there may be some local operators and there may be a difference in how we enclose the line. In this case, we think about the boundary as a non-genuine. So the boundary is not a codimension two operator because it has a sort of a branch cut. So we cannot specify correlation functions given just the boundary. We need to specify more data. This is the case of a 't Hooft construction of 't Hooft lines. So when 't Hooft constructed 't Hooft lines, in fact, he constructed boundaries of topological non-trivial surfaces. So he did not construct lines. He constructed boundaries of topological non-trivial surfaces. And you might remember the fundamental equations from 't Hooft papers. So the fundamental equation in 't Hooft's paper was like that. And then there was some phase. You might remember this equation where T was a 't Hooft line and W was a Wilson line. And then 't Hooft struggles for a whole page in the paper explaining how come, if the two lines are at equal time, how come we get a non-trivial commutator? Because equal time commutators must vanish if they don't intersect. So there's a whole struggle. But the explanation is that his 't Hooft line is not is a boundary of a surface, and then it does intersect. So at equal time, there is a phase. So 't Hooft lines are not deemed genuine lines. They depend on some additional data, which is the filling surface. And that's why 't Hooft got this equation. So in fact, the fundamental equation in 't Hooft's paper should be really interpreted in the language of one-form symmetry. So what 't Hooft really said is that there is a topological codimension 2 surface that pinches the Wilson line, and you pick up a phase. So he really just did that. So SUN Yang-Mills theory with an adjoint fermion will have such an operator. So basically, the first example goes back to 't Hooft. So it's Yang-Mills theory with an adjoint fermion. So that's the simplest example that has such a codimension 2 operator. And well, it's the same equation, but the interpretation is different nowadays. We think about it in this more abstract language of 2 groups and so on. Are there any questions? Okay. Well, sorry, I'll just go to that one.
Now, the non-abelianness of the 0 form one does not mix in with this form?
Yeah, it could be that the 0 form symmetry is non-abelian, and then in general, you'll have to disentangle. I mean, generally there will be a 2-group symmetry if there are both objects around, and you have to disentangle it. And
no, what I'm saying is that analog of the 2 lines is no longer abelian. Or is it?
It is abelian.
How do you argue there now? Because the argument that you had before with this goes to true.
But it's the same because in Yang-Mills theory with an adjoint fermion in 4 dimensions, there is a Zn symmetry.
For that example, I'm just asking a general statement.
Yes.
You see that this is always abelian now?
This?
Yeah, you showed that if you didn't have that boundary, you could move them away to abelian. Now if it's
No, the boundary is artificial. What 't Hooft has really been discussing is what happens when you take this surface. So the boundary is not necessary for 't Hooft's for what 't Hooft said. The way to interpret what 't Hooft said is that you take a closed surface.
I'm not asking about the truth at all.
Okay.
I'm going back to your derivation of there.
This one, yeah.
The fact that you said that this is always abelian.
Yes.
And your argument was that, look, you can just maneuver them.
Yes.
There's nothing preventing. Now, if there's a sheet attached to one, you can't do that.
Right,
so
but
it's no longer obviously abelian.
But I'm just discussing closed surfaces.
No, but in this context.
Right, but this is different. You can ask what happens when you take a codimension 1, a non-trivial topological operator, and you define a boundary. That I do not call a codimension 2 operator.
Well, whatever it is, it can have non-abelian structure.
With a boundary?
Yeah.
Yes, but this is a different object. I'm not discussing this.
Has that been studied?
Well, a 't Hooft line is an example.
But that's an abelian example version of it. Has people have studied non-abelian version of that?
Let me. Perhaps nothing comes to mind. But I'm going to. For me, these sigma surfaces are always going to be closed surfaces. No. I'll give you examples in any dimension of this phenomenon. I mean, so far it's just definitions. We didn't do any dynamics, but soon obviously, for example, this symmetry imposes restrictions on the dynamics of such theories. So we'll discuss dynamics soon. So far, it's just an introduction. So there is a general way in which this one-form symmetries can arise, and that's how this is connected to this workshop. So general construction. This is by far not the only way in which such symmetries arise, but this is a general construction. So suppose you have a gauge theory in any number of dimensions. Suppose you have a gauge theory with some gauge group G, and the gauge group G has a center C. So C is the center of the group. And suppose there is a subgroup of the center, gamma is a subgroup of the center, which such that gamma doesn't act on the matter fields. So this is a very Lagrangian construction. We're talking about matter fields, gauge groups, and so on. This is a very, very Lagrangian construction, but it's invariant under dualities, for example, which it's an interesting check, for example, in S duality, to see that gamma agrees on both sides. C is the center. C is the center of the group, and gamma is a gamma is a subgroup of the center that does not act on the matter fields. So by definition, this is abelian, and therefore also gamma is abelian. So in this construction, gamma is going to be a one-form symmetry. So there will be codimension 2 surface of codimension 2 topological operators whose algebra is gamma. So this is a very general construction, and all the examples that I'll give in 2 and 4 dimensions are going to be of this type. In 3 dimensions, we'll see another example, a more interesting example. This is just one way to construct theories with such a symmetry. And now it's obvious why this is connected to the workshop, because, well, if the lattice of charges is not populated, then there is a gamma. So when the lattice of charges is not populated, then there is a new global symmetry. So I should emphasize, perhaps, that these one-form symmetries are just ordinary global symmetries, like zero-form symmetries. So if you don't like global symmetries, you may want to assume that there are no one-form symmetries, and therefore the lattice of charges must be populated. So it's.
I mean, for ordinary global symmetry, there are some arguments based on black holes. Is there a similar? What is the argument that there should be no global one-form symmetries in zero quantum gravity?
Well, for discrete symmetries, even for zero-form symmetries, the arguments are not as sharp. They involve maybe, well, there are some arguments which are indirect on based on ADS. Well, with one-form symmetries, the argument could be that you will have stable strings that are not protected by any gauge field, and you may not like that for some reason. I don't think that there is a solid argument. I'm just saying that the way this subject is connected to the workshop is through this observation. So if you don't like global symmetries, it has an implication for filling out the space of charges for some gauge theory, which is an interesting correspondence. Okay. So basically, the intuitive reason is that if there are no charged particles under some gamma, there will be some representation R such that we can construct the path-ordered exponential, the Wilson line in that representation, and this will not be screened. So this cannot be screened because there are no particles that would carry a representation that's in the same anality as R. So this cannot be screened. And those Wilson lines, when they act on the Hilbert space, they will create stable strings. Well, they will create some strings when you act with these things on the Hilbert space, and these strings would not decay. So in QCD, let's say adjoint QCD or pure Yang-Mills theory, there are such strings. We'll discuss them perhaps at the end. They are protected by one-form symmetry. They've been studied to death on the lattice. They're called K-strings by the lattice community. And there's a huge amount of literature on those strings. They're protected by discrete one-form symmetry in QCD. So this is the intuitive reason why there are such. Well, and then, so there is a global symmetry that protects these guys from decaying, essentially. Okay, so this is some general introduction. And I want to go by just over some interesting canonical examples of interesting systems with some dynamics in 1 + 1, 2 + 1, and 3 + 1. Yeah, I have never studied the one-form symmetries in that situation, so I don't know much about it. I'll start with 1 + 1 dimensions.
Would you imagine that there is a bound at 6?
Yeah, I have no idea. I've never studied what happens. What are the consequences of these higher symmetries in higher than 4 dimensions? Are there any questions about the general introduction? Just the setup of what we mean by higher form symmetry, one-form symmetry. And okay, so now we'll do some 1 + 1 dimensional example. And here, this is connected to another aspect of the weak gravity conjecture. So in 1 + 1 dimensions, a one-form symmetry is generated by what? See, we need the topological codimension 2 surface. What is the topological codimension 2 surface in 1 + 1 dimensions? It's a point, right? So in fact, in 1 + 1 dimensions, a one-form symmetry is just a local operator. So it's just a local operator which is topological. What is a topological local operator? A topological local operator is an operator whose correlation functions are independent of its location with respect to other operators.
Why does it have to be local? Why can't it be
Collection of points. Yeah, you could insert this operator at multiple points. I'm assuming that this is a connected closed manifold throughout.
Sure, but if you look at some...
You said connected, so we are done. You cannot have manifold. The connected definition of sigma.
Well, I've not given any definitions. This is just an intuitive explanation. There are many points here where I skipped the subtle issues. So it's just a topological operator, okay? Now, a topological operator is, if you think about it as a type 1 von Neumann algebra, then it wouldn't work because you have a center. So this is in the center of the von Neumann algebra. And this is a crucial ingredient in what Hiroshi explained last week. So we see that having a center is not such an esoteric construction. Anytime you have a one-form symmetry, there will be a center to the von Neumann algebra of local operators. So why are these operators important? Where they don't talk to other local operators, but they talk to lines. So you can again compare like OX with a line, compare it with the line sitting on the left-hand side of the operator. And that would typically be related by some transformation G of the line. Okay? So if we have some lines if we have good line operators and we put a local operator, then there will be this kind of algebra. O on the left is the same as O on the right with G acting on the line. Okay, so now we'll see some cool examples of this phenomenon. I'll construct some explicit examples based on two-dimensional QED. First, we'll do just pure Maxwell in 2 dimensions. We'll analyze pure Maxwell, construct this operator, and then we'll add matter fields, which are fluctuating. And you'll see that it leads to really interesting dynamics. And some of it has been also observed on the lattice. So it's not science fiction. Good. So now we're going to study 2D Maxwell. It's a very pedagogical, pure Maxwell, no matter fields, 1 plus 1D Maxwell. It's a pedagogical example that you can cover in a graduate course. But I'm going to walk you through that anyway. So we have f wedge star f plus theta over 2 pi f. This is the Lagrangian that we're going to study. It's a 2D Maxwell, no matter fields, and a theta term. And you might remember that theta is 2 pi periodic because the Chern class is quantized. So let's quantize this theory. As you know, there are no propagating matter fields. There are no propagating matter fields. There are no propagating degrees of freedom in infinite space. So we can put this theory in a circle to quantize it. So let's take let's study the theory on a circle of radius r. Okay. So in that case, there are some degrees of freedom that cannot be gauged away, because the integral over S1 of the connection is a physical observable mod 2 pi. So the holonomy cannot be gauged away. The holonomy is physical. So the quantum, sorry, I'll call this Q. So the variables in the quantum mechanical model that we will get after reducing this on the S1 are just the holonomy. So the Lagrangian in quantum mechanics is going to be Q dot squared, and you can just check it at home. And R is the radius of the circle. So this is equal plus theta over 2 pi Q dot. So this is a particle. Q is a periodic. Q is an angular variable. So this.
So the characterization is assumed. I mean, you have some charge in principle, right?
No, there is no charge. This is the model without any charge. I want to show you how the one-form symmetry arises. What are the consequences in this very pedagogical example? There are no charged particles here. It's just pure Maxwell. I'm just trying to quantize pure Maxwell.
You assume it's a U1 connection.
I'm assuming it's a U1. Yeah. It's a U1 gauge theory. No, there is no charges. The gauge, first we choose the gauge group, and then we choose which representations to add. In particle physics, often it's confused. People choose which representations to add, and then they choose the gauge group according to that. But it's the other way around. The gauge group is more fundamental than the representations. Okay? In particle physics, it's the opposite. Like people try to infer the gauge group from the representations. So it's not very logical. And in fact, we don't know what's the gauge group of the standard model. You know that? So it's not. So people often say that the gauge group is this, but we actually don't know that this is true because there could be a Z6 here, or there could be a Z3, or there could be a Z2. There is a Z6 ambiguity in the standard model gauge group, which affects the one-form symmetries that the standard model has. So we don't actually know the gauge group of the standard model, and it affects which monopoles can exist. Some of it is inconsistent with grand unification. Some of it is consistent. Okay, so there is a question of how do we find out what's the right gauge group of the standard model. We cannot do it from low energy experiments very easily. We need to know monopoles or GATT or something of that sort. Okay. So the quantization of this model, Q is a periodic variable, as I said. Q is defined. So this model is just a particle on a ring with some magnetic flux, a Aronoff-Bohm flux theta. So we have a particle moving on a ring, but every time it goes around, it picks up a phase. And so the energy levels can be easily found to be n plus theta over 2 pi. This is the nth energy level. And this is multiplied by E squared r. R is the radius of the circle. Squared, sorry. Yes, thank you. So if we draw the energy levels, we'll get a parabola here, and then another one. So it will be I'll center it here. So I'll just draw it like this. And then another one, and so on. Yeah. And now I'll try to explain to you what's the physical significance of this. This is exact, right? This is an exact quantization of 2D Maxwell. So observation number 1 is that notice that all the energy levels are extensive, exactly extensive in the size of the S1. That means that there are no propagating particles. It's all just vacuum energy. It's just vacuum energy because it's all extensive. So this theory has many superselection sectors, but no propagating particles. So once you decompactify the theory, one way to think about it is that we have many superselection sectors, but there is no way to tunnel from one superselection sector to another because there are no propagating particles that can facilitate the tunneling process. So we have infinitely many superselection sectors. So it's as if you had a scalar field with many metastable minima, right? That's an analogy. So we can think about this as a star F. This is the electric field. I haven't yet. So the order parameter for this different minima, is the electric field star F. You can just compute the derivative of the energy with respect to theta. And this is the electric field because theta couples to the electric field as here.
Why don't we just dualize the 2 form to 0 form?
Then it would be immediate, right?
Yeah, that's what I did. So this is a 0 form. So this basically the physics here is that you have a potential like this, but there is no way to tunnel. So you should think about these barriers as infinite. But there are infinitely many superselection sectors in 2D Maxwell. And the order parameter is the electric field. It's a constant electric field. So it's the density of the electric field. And now, at theta equals pi, as Samson mentioned, at theta equals pi, there is something special. 2 superselection sectors are exactly degenerate. So there is another one here, and they're exactly degenerate. There are 2 exactly degenerate superselection sectors, even on a circle. So 2 superselection sectors are exactly degenerate. So 2 vacua. Instead of saying superselection sectors, I'll just say 2 vacua. We're now decompactifying S1. So 2 vacua are exactly degenerate. This is at first sight perhaps odd because you know that if you have a QFT in infinite volume with 2 degenerate vacua, when you put it on a circle, typically the degeneracy is lifted. Like in any reasonable quantum mechanical model, there is no more degeneracy once you compactify it on a circle. But this is in this example, the degeneracy is not lifted because there are no instantons. This model doesn't have any propagating particles, and propagating particles are like instantons. Or more precisely, we can think about this potential barrier as being infinite. So it's not lifted even when you put it on a circle. This is somewhat weird, but true in this example. Now, what is the symmetry what is the symmetry between these two vacua here? The symmetry is charge conjugation. So at theta equals pi, there is a charge conjugation symmetry that takes the electric field to minus itself, because the theta equals pi is the same as minus pi mod 2 pi. And so there is a spontaneous breaking of charge conjugation symmetry. So this is the physics of pure Maxwell. The take-home message is that there are infinitely many vacua, but there is only one global vacuum at generic theta. There is only one. At theta equals pi, there are two exactly degenerate vacua. So it's very similar to the physics of Ising-like systems or other systems, except that there is no way to tunnel from this higher vacua to the lower vacua. So it's as if you take an ordinary QFT and you just make the potential barriers infinite. That's the physics of 2D Maxwell. Now I want to get to the one-form symmetry. Are there any questions about the quantization of 2D Maxwell? OK, so now I want to discuss a little bit the one-form symmetry. Yes, yes. N equals 0 and n equals minus 1 are exactly degenerate for theta equals pi. Well, yeah. So they're exactly degenerate. So it's a system in which there is charge conjugation symmetry at some theta. It's spontaneously broken, which is fine. We're in 1+1 dimensions. We can break discrete symmetries. Otherwise, there is just one vacuum, and that's it. So the only peculiarity of this theory is the fact that there are all these other superselection sectors that are exactly stable, even though they have a higher energy. And so what is the one-form symmetry? Now we'll see how this ties nicely with the one-form symmetry in this model. As I said, in this model, what is the center of the group? It's U1, because the whole group is U1, so the center is U1. But there are no charged particles, so also gamma is U1. So the one-form symmetry here is U1. It's a nice abelian group. And we can construct it explicitly via Netter's method, because it's a continuous symmetry, so we can construct it. So what is the operator that is independent of the distance? Let's see if somebody is still coupled. Does anybody know which operator in this theory is independent of position? Very good. Electric field was constant. Nikita is still listening. So star F. Star F is a nice local operator, completely independent of position, because the electric field has to be constant in any vacuum. So star F is exactly conserved. And you can just raise it to the exponential. And that is, with some coefficient alpha, I alpha. And this is going to be the generator of some rotation by angle alpha of the one-form symmetry. And you can there is a small homework exercise. Let's put the electric field here, the electric field operator here. Then we put the Wilson line in the fundamental representation. What is going to be the electric field on the other side? This is called Gauss's law. So the Wilson line can be viewed as a probe particle of charge 1. We don't have such propagating particles, but we just put a probe particle of charge 1. So if we have an electric field E, then on the other side, we're going to have star F plus 1. OK? So this is an example of how Wilson lines transform when you move the one-form symmetry generators across them. So once you raise it in the exponential, it can be interpreted as a transformation rule of e to the I alpha. So it's just the electric field jumping by 1. You put it in the exponential. It means that e to the I alpha, e to the IA transforms by e to the I alpha, e to the IA. So we can think about it as a U1 action on the fundamental Wilson line. OK? So this is a silly example, but it has a very interesting physical interpretation. This is the electric field. It jumps by 1. We have a U1 one-form symmetry. And this can also be understood as a non-dynamical domain wall between vacua where the electric field is E and vacua where the electric field is E plus 1. So we can go back to our picture here. You remember this picture, for like this qualitative picture for all the vacua of pure Maxwell? So the Wilson line allows us to jump from here to here. So this is what the fundamental Wilson line allows us to do. And you can also go back. Because it's an invertible thing, you can also go back. So the Wilson line allows you to increase the electric field every time you put it. It's a domain wall between different vacua. Okay, so this is just pure Maxwell. But now I'll tell you something new. This is just a reinterpretation of obvious things. Right, but this is not dynamical. So this is like you just bring from infinity a huge massive charged particle. It doesn't fluctuate. You put it. The Gauss law would just shift the electric field by 1, and you can interpret it as a transformation rule of the Wilson line. So we cannot tunnel physically from this vacua to this vacua, but we can interpolate between them by putting defects, Wilson lines. So this is a simple construction of a one-form symmetry. Just pure Maxwell. Now I'll tell you something not obvious. You'll see why one-form symmetries are deemed interesting, why people want to study them. So now I'll do something non-trivial. Something that I cannot demonstrate analytically, but you can demonstrate it by abstract arguments. Let's suppose that we've now added some matter fields to this theory. So let's add matter fields. So I'll study two situations back to back. One case is where we have an electron of charge 1. So this is a charge 1 electron. This is ordinary QED. It was studied in the 70s. And the other case, we'll study a charge 2. We'll add a charge 2 electron. So the only difference is just a factor of 2 inside the covariant derivative. And that's it. So I'll try to show you back to back these two examples. And you'll see how these one-form symmetries affect the dynamics. So let's start from this, in fact. This model is an interacting model where there is a Z2 one-form symmetry. Because the charge lattice is not completely populated, we don't have propagating charge 1 particles. So there is a Z2 one-form symmetry. And now we cannot write it explicitly, because star F is not a topological operator anymore. We have dynamical charge 2 particles, so they can be created from the vacuum. And therefore, star F can jump by like 2 units. And therefore, star F is not a topological operator anymore. So we cannot write it explicitly. It's a discrete symmetry, but we know it exists. There is some Z2 one-form symmetry. So here, for example, there is a claim that a theta equals pi. Yeah. Right, but that would not be a topological operator, because star F can jump by 2 units due to the creation of particles from the vacuum. Yeah, you can. I'm just saying that star F is not conserved anymore. You can try to write this thing. This will be fine. This will be well defined. But yeah, we don't have the analog of a topological operator like this. We cannot write it like an exponent. Well, this is good enough, I guess, for the purposes of what you want. So that would be fine.
How would you treat the D8 by D8 by is it
D8?
D8 in type 2. So it does lead to jump.
Yes. Yeah. The space-filling branes or codimension 1 branes, if they are stable, they can be interpreted in this language.
You think of them as heavy objects and then non-dynamical?
Yeah, it depends if they're dynamical or not. So one has to make this crucial distinction. So let me just make some claims, and I'll explain in more detail where does that come from. So if we have a dynamical charge 2 particle, it turns out that, well, you can add a mass. In both cases, we can add a mass to this electron. That we can just add this term in both cases. So here, the claim in this case is that due to this Z2 one-form symmetry, the claim is that at theta equals pi, you remember that at theta equals pi, we had 2 exactly degenerate vacua, where the electric field here was -0.5 and the electric field here was +0.5. So since we don't have dynamical charge 1 particles. The claim is that at theta equals pi, we have this exact degeneracy. So charge conjugation is broken spontaneously at any mass. So you can prove an exact result, even about strongly coupled QFTs, using one-form symmetries anomalies. I'm not giving you the proof, but the proof is that since intuitively, since there are no charge 1 particles, you might expect that the charge conjugation symmetry here is broken, and these guys would not be lifted. So this is an example for dynamics that you can check on the lattice. In this case, in fact, for a large M, charge conjugation is broken, and for small m, at theta equals pi. And for small mass, charge conjugation is restored, and there is an Ising transition, a 2D Ising transition between the two cases. So there is some m star where there is a 2D Ising model. It's a second order transition. So it's not like a cosmetic difference. You might think the charge 2 and charge 1 is the same, but I'm not explaining why. But the point here is that it's not a cosmetic difference. The actual dynamics of the theory changes. Here there is a second order transition between a phase where at theta equals pi there is 1 vacuum and 2 vacua, and here this 2 vacua is robust. You cannot get rid of it. So there is no Ising transition. Well, no, it's not a universal quantity, I believe, but well, we made this prediction, and lattice people agree that this is true. For example, there are some works by Nahum and others also supporting this conjecture. So it's not a cosmetic difference, and it's not so hard to construct examples where there is a one-form symmetry, even in interacting models. Now I'll tell you what I'm going to do next. The next thing that I want to do is to tell you how one-form.
This is close to models that you might imagine realizing that this from mechanical model.
Yeah.
So this has been, could this realize this transition in some material or something?
Yes, this example is pretty easy to. I mean, I don't know about materials, but you can write it down on the lattice, and you can check that this is true. The fact that this is true is not obvious. The reason I'm telling you these facts is because you might have the prejudice that perhaps this doesn't matter if it's charge 2 or charge 1. So I'm just telling you that the actual dynamics is not the same. So it really matters. So the next topic that I'm going to describe next, the next topic for the next hour is the Chern-Simons. And I wanted to explain how one-form symmetries work in Chern-Simons theories, which is a slightly less obvious thing. So it's one-form symmetry in Chern-Simons theory. And then I'll make some comments about one-form symmetries in 4-dimensional gauge theories.
There's another one, just in Chern-Simons, which would be 2D.
Okay.
2D WZW with a boundary.
Let me.
Group, particle in a group, basically.
Yes.
But you have a B field.
Let me think.
I think there is a boundary. It has, I believe, similar.
But in what sense? What is?
You need to complement it with a boundary to make it well defined.
But why ill-defined? Here, these are well defined.
The boundary addition is arbitrary.
But how is this connected to this? This was not without boundary. These are like, this is the dynamics of the system in, infinite space without any boundaries.
Right. That is similar in the sense that the effect with theta terms that you have for a particle takes place because there is a natural B field.
Yeah, I know what you mean. You're saying probably that that you need a projective representation on the domain wall. Yeah, that's correct.
The similar effect will take place.
Yeah, that's correct. But there is no one-form symmetry in the bulk. Here there is a one has to distinguish two different issues. One is whether when you put these walls, there is a projective representation on the wall, and the other subject is whether there is a one-form symmetry in the bulk.
No, that one exactly will not have one.
Yeah. But you're right. But that's right that the boundary conditions will have a projective representation of G. Yeah, that's correct. Okay, so next I'll just try to tell you how one-form symmetries work in Chern-Simons theories. We'll discuss SUN level K and U1 level K. It's just an example so that you see how maybe it fits into the weak gravity conjecture in some way. And then I'll just give a few examples of 4D gauge theories, again, without explanation, just facts. I don't have time to prove these statements here. Okay, take a break now. Okay, I'll just start with a small comment. Several people during the break asked me, how is this claim consistent with duality? So let me just tell you again the claim. Maybe it's a comment for the experts more than part of the lecture, but since several people asked me that, I thought it's worthwhile to spend 5 minutes on that. So the claim that was that if you couple QED to a charge 1 fermion at theta equals pi, then in this case we have a 2D Ising transition, a second order transition where at large mass charge conjugation is broken. We have 2 vacua with electric field minus a half and half. And in that case, there is no symmetry breaking and you have a second order transition. And while in the other case where there is a charge 2 fermion, my claim was that this Ising transition is removed. And instead you have a charge conjugation symmetry breaking for all mass. And the question was, how is it consistent with duality? So I'll just spend, it's a comment for the experts. This is like an interesting example where you can see how one-form symmetry plays with duality. So in the first case, the duality is well known. The duality of QED coupled to a massive charge 1 fermion. It's well known that this is dual to basically, like a Sine-Gordon model. So it's basically a scalar. It's basically a massive scalar field. At least when the mass is when the mass of the electron is very small, this is the boson mass. When the mass of the electron is very small, it's just a massive scalar field with mass e squared, and there is just one vacuum. So this is in the limit where the mass of the fermion is very small. You can just dualize the fermion and the gauge field, and you get a sine Gordon. Well, you just get the massive Klein-Gordon model. It's even simpler than that. We just get a Klein-Gordon model of a massive scalar field with one vacuum. On the other hand, when the electron is very heavy, we have 2 vacua because we can have the electric field being either a half or minus a half. And so we have one vacuum when the fermion is very light, and when the fermion is very heavy, we obviously have 2 vacua, because in that limit it's like pure Maxwell. Yeah, it's just like pure Maxwell in 2D, and there is a spontaneous charge conjugation symmetry breaking in that limit. And you can actually prove analytically that the transition is second order, and it's in the universality class of the Ising model. So this is the ordinary duality, and that's that's what the ordinary bosonization would tell you. But now it's interesting to ask what happens in that case if you do bosonization. Actually, the interesting thing is that, well, this is not modified. This is just the limit where the theory is approximately given by pure Maxwell. But this is modified. So the bosonic dual in this case is slightly different. You have to follow the fact, you have to be careful about the fact that there is a charge 2 particle rather than charge 1 when you bosonize. And what you find instead is a Klein-Gordon field coupled to level 2 BF theory. Level 2 BF theory in 2 dimensions, and so it has 2 vacua rather than 1. So in the other case, you have to replace that by that, and there are 2 vacua at any mass, and there is no transition. So the Ising transition is lifted. And the one-form symmetry, Z2 one-form symmetry in this duality frame becomes, in this duality frame, something completely different. It's a global symmetry of the BF theory. So you see that one-form symmetries that are associated to unpopulated charge of lattice charge under duality can become something completely different. Okay, so one can do this duality. One can do this in great detail and prove the statements that I made here. Now I want to tell you how what.
Can we just see this by superimposing the quadratic potential or the cosine potential?
Yeah. So in the first case, this is if the fermion is extremely light. If the fermion was not so light, if the fermion had finite mass, we would just add like the fermion mass times some cosine of phi.
You can just see that the potential. Just change it. You change the parameters of the potential. You see two like that here.
Ah, yes, very good. Yeah, so if you follow this duality, if you follow this duality, like, beyond its naive regime of applicability, you can see that these two guys cancel each other, and you see this transition. And it seems second order, but then you have to take into account quantum fluctuations, which may or may not remove it. And you can actually prove analytically that it's still second order in the full quantum theory. This is non-trivial. This is a non-trivial argument. But here, the duality also involves an additional term, where you couple phi to a Z2 gauge field. And that splits the transition, even at small mass. Very good. So indeed, as Nikita said, you can see the transition at this level very nicely. Very good. So, okay, now I want to just tell you a few things about one-form symmetries and Chern-Simons theories. It's not going to be anything deep. It's just a small introduction to show you how one-form symmetries arise in 2+1 dimensions in Chern-Simons field theories. And in Chern-Simons matter theories, obviously. So one-form symmetry in 2+1D. So one way, okay. So I'll do two examples. One is going to be an abelian Chern-Simons theory, and one is going to be a non-abelian Chern-Simons theory. Those examples work a little bit differently than those because, the Chern-Simons section is not gauge invariant, and it introduces some interesting complications. So we'll start from the abelian Chern-Simons theory, k over 4 pi, integral a wedge dA. So if we follow our nose, I said that if we have a gauge theory with group G, and there are no matter fields charged under the center of G, then the center of G would be the one-form symmetry. Here, there are no matter fields. It's just pure Chern-Simons. But the one-form symmetry is not U1. It's actually ZK. That's what I want to explain today. That's what I want to explain now. I want to show you that the one-form symmetry here is ZK, where K is the same K as here, and it's an integer. Okay. So that's the first thing I want to show you. This is true in the abelian theory. And then we'll do some non-abelian examples where it works differently and in a more interesting way. So let's see why it's true. And then I'll show you an application. I want to show you one application for an interesting condensed matter system for this thing. So it's not going to be a completely vacuous discussion. So we can define the following Wilson lines. WQ is e to the I q integral of A over some curve gamma. And the algebra of these Wilson lines is well known. So if we take WQ prime, it's the same as WQ prime, WQ e to the I 2 pi Q prime over K. And here we're assuming that they're wrapping each other. So it's like, something like this. So here we're assuming, they didn't wrap each other. So we're just doing this thought experiment where we're braiding them across each other, and then we get this formula. Now, this formula can be interpreted in the language of one-form symmetry, because WQ satisfies, so these W's can be viewed as one-form symmetry charges. There are topological lines, as we need, and they obey this algebra on W. So we can think about this equation in the following interesting way. We can think about WQ as W1 as the generator of ZK one-form symmetry. ZK because the charge lines transform under zk and not under U1. So faithfully. So zk acts faithfully. You could say that the one-form symmetry is U1, but it wouldn't act faithfully. This acts faithfully. So an interpretation of this well-known formula is that W1 is the generator of a zk one-form symmetry. And then the same generators play somehow also the role of being in a representation of zk. And the same WQs can be viewed as being in a representation of zk. So you can imagine fixing Q prime and then varying Q, and then Q prime is in a irreducible one-dimensional representation of zk. Can be viewed as in a zk representation of zk representation. Okay, so it's just a reinterpretation of a well-known formula. We just say that the W's are both the charge fields, but also the generators of the one-form symmetry. And the reason it's not U1 but zk is because this is the subgroup that acts faithfully. Now, question is, how does it work in non-abelian Chern-Simons theories? So what is the one-form symmetry of, let's say, SUN level K? So let's now discuss the one-form symmetry of SUN level K. So does anybody have a guess? What is going to be? So the answer is Zn. So this is the one-form symmetry of SUN level K, and this is true for any K. So let me explain what it means. So so this theory has many lines. There is some rule of which Young tableaus correspond to interesting lines in this series. But the idea is that there is a subset of the lines. There is a subset of the lines that they are of course they are topological, and and all the other lines can be viewed as in representations of that subset, such that all the other lines are in a representation of that subset, and that subset of lines also satisfies a similar subalgebra like that. If you just restrict your attention to that subset, it satisfies an abelian subalgebra. So it's an abelian subset. And you can you can show that for SUN level K, that subset is isomorphic to Zn. Now, okay, so level rank duality would relate this to UK level n, right? That's what level rank would mean, minus n if you want to be precise. And this is the same as SU K level n times U1 level Kn divided by Zk, right? So this has Zk, one form. So if you accept this rule, this has a Zk subalgebra of abelian anyons, under which everything is in a representation. According to our previous discussion, this has Zkn. And then when you divide by Zk, you have to project out all the Zk's here with the Zk's here, and you get a Zn. So dividing by Zk is like removing K-squared lines. So there is a Zn one-form symmetry on both sides of the duality. Okay, so the claim is that SUN level K has a Zn abelian subalgebra of lines, such that everything is in irreducible, can be viewed as in irreducible representations of this Zn symmetry. And now I'll give you one more fact, which is going to be useful for some examples of dynamics. This fact I would not prove. So one-form symmetry, like zero-form symmetry, can have anomalies. They can be spontaneously broken. You can try to gauge them. They're very similar to zero-form symmetries. So the fact is the following, that for U1 level K, the one-form, I'll just write it in the following way. So fact. This is the fact in 2 + 1 dimensions. If you have a ZQ one-form symmetry, the anomaly takes values in ZQ. So there is another ZQ where the 't Hooft anomaly takes values. So for any system, it could be a Chern-Simons matter system, or it could be a gauge theory. If you have a ZQ one-form symmetry, the 't Hooft anomaly takes values in ZQ. So for some applications of anomaly matching of one-form symmetries that I'll explain in a second, I want to quote the values of the anomaly in these two examples. So I can spend 5 minutes explaining the mathematics of where this ZQ comes from. Does anybody want to see why this is true, or I should proceed? If anybody wants to see the proof of this, I can spend 5 minutes. Raise your hand if you want. No? Or yes? So you should think about one-form symmetries as essentially like zero-form symmetries. How do we detect anomalies? We try to gauge. We try to gauge those symmetries. So we try to gauge. Okay. Now, when we discuss zero-form symmetries, we try to gauge zero-form symmetries by coupling them to a one-form connection, to a gauge field. For one-form symmetries, we try to gauge them by coupling them to a two-form gauge field. Two-form gauge field. So we need a two-form gauge field, okay? Now, if the underlying one-form symmetry is ZQ, the two-form gauge field has to be a ZQ two-form gauge field. So we need a ZQ two-form gauge field. This is mathematically basically an element of H2 X Z Q. That's a two-form gauge field. And now so let's denote this guy by B. This is a two-form gauge field. So how do we classify anomalies in 2 + 1 dimensions? As the anomaly inflow procedure has taught us, it's enough to classify possible four-dimensional actions. That's why there is a 4 here, which involve B, a pure functional, classical functional for a two-form gauge field B. So you have essentially what you can write is B cup B, where cup is the usual cup product between objects in this cohomology. And now the claim is that you can put 1/n here, and then 1/q here, and any integer p. So let me explain why this is true. You can think about B intuitively as valued in ZQ. So it's 0 to q minus 1. So what are the requirements from these coefficients? Well, it has to be an integer over q, because B is only defined mod something that's a multiple of q. So if we shift B by one of the B's by q of something, then this has to be the whole thing has to be an integer, so that the exponential of this thing is well defined. And therefore, P has to be an integer. So that, and also if P is a multiple of Q, this is trivial, because it will just take integer values for any configuration of B. So therefore, P has to be an integer mod Q. So the anomaly is classified by an integer mod Q. Yeah.
Wouldn't you also write Pontryagin square?
Yeah, you could write Pontryagin square, which would in fact enlarge the answer to 2Q. But so I've made like many little technical assumptions that I haven't said. I'm discussing spin TQFTs. For spin TQFTs, you cannot write the Pontryagin squared. It's only for bosonic TQFTs with even Q. But I'm discussing spin TQFTs, and so it's just this. Yeah, for your Pavel, right? Yeah. So what Pavel said is that for even Q, if you have a bosonic TQFT, the answer is Z2Q. And this 2 is very hard to see. You need to use the Pontryagin square, not the ordinary cup product. Okay. But that's what we will need for the discussion today, because I'll discuss Chern-Simons matter theories with fermions. So I won't need that little loophole. Okay. So now I'll tell you the answer for what is P for Chern-Simons matter theory. It's an interesting question to try to, work it out for generic Chern-Simon symmetry theories. But I'll tell you the answer for SUN and for U1. So for U1 level K, we said that the one-form symmetry is isomorphic to ZK, and the anomaly turns out to be 1 mod K. So you cannot gauge the ZK one-form symmetry. And for SUN level K, we said that the one-form symmetry is Zn, and the anomaly turns out to be K mod n, if you think about it as a spin TQFT. So this is 1 mod K, and this is K mod n. I'll need these two facts when I show you some applications now for anomaly matching of one-form symmetries. Actually, there is an easy way to see why this is true, and there is a somewhat natural way to see why that is true. So notice that if K was n, if we had SUN level n, then this would vanish. That basically means that we can gauge the one-form symmetry. Gauging the one-form symmetry means that we're quotienting the gauge group by Zn. So we'll have PSUN level n. And that concept makes sense only when the level is a multiple of n. So PSUN Chern-Simons theory only makes sense when this is a multiple of n. And that's why there is no anomaly when K is equal to n. That might have been too hard to follow, but I don't have much time to explain. I'll just show you an example of how anomaly matching works. I'm not trying to explain everything pedagogically. So, examples. So we'll do two examples of Chern-Simons matter theories where we'll use these results. So the most interesting example is an example that arises in the context of the quantum Hall effect. It's called the thing. I think it's called the 5 halves, the 5 halves state of the quantum Hall effect. So I wanted to describe this theory in the language of high energy physics, and we'll use some of this business to understand its low energy dynamics. So the theory is U1 Chern-Simons theory at level 0. So the bare Chern-Simons coupling is 0, plus a charge 2 fermion psi. So it's again a system where there is a fundamental particle of charge 2. Because we don't have fundamental charges that are dynamical, we have a Z2 one-form symmetry. And we'll use that one-form symmetry to learn something about the infrared. So let's write the Lagrangian. The Lagrangian F is F wedge star F plus psi dagger d psi, where this is a charge 2 particle, so the covariant derivative is appropriate. And then we have a mass like this. And the mass could be any real number. It could be either positive or negative or vanishing. In fact, if the mass is vanishing, it's an interesting special case, which because the theory also has time reversal symmetry when the fermion is massless. So we have time reversal if the mass is 0. So let's try to analyze this theory. As a function of the mass. So when the mass is huge, it's easy to analyze using effective field theory techniques, standard effective field theory techniques. So when the mass is huge and positive, the fermion is non-dynamical. We can just integrate it out, and it shifts the Chern-Simons level, which is initially 0. It's shifted to something. So do you remember how much you need to pay if you integrate out one fermion? How much is the Chern-Simons shifted? By 1/2. Great, but this is a charge 2 particle. So it's actually shifted by the square of the charge over 2. So it's shifted by 2. So here we have U1 level 2, pure Chern-Simons theory. So this is what the theory flows to at very long distances when the mass is huge and positive. We just get a pure Chern-Simons theory, U1 level 2. Very far away here, you just get the opposite because the mass is huge and negative. So you get U1 level minus 2, Chern-Simons effective field, Chern-Simons theory. And now there is a very amusing fact that you can understand through these anomalies. which is that let's just consider for a second so the Z2 one-form symmetry is visible clearly because, as I told you, U1 level 2 has a Z2 one-form symmetry. So we see the original Z2 one-form symmetry very nicely in the infrared. The anomaly at very large mass is 1 mod 2, according to the formula I've given you here. When the mass is minus infinity, on the other hand, the anomaly is minus 1 mod 2 because the level is reversed. But minus 1 mod 2 and 1 mod 2 are the same, right? So we see a funny example of anomaly matching. The one-form symmetry anomaly nicely matches in this semi-classical regime, which it must, otherwise there is an inconsistency. But since these two theories have the same anomaly, in fact, one is compelled to guess an identity between Chern-Simons matter theories. And in fact, this is true as spin TQFTs. So in fact, U1 level 2 and U1 level minus 2 have exactly the same anyons. Exactly the same spins, exactly the same anyons, exactly the same algebra of braiding. So in fact, we don't need to put a minus here. We need to put a plus. We can put a plus if we like. It's the same theory. So this is an accident for U1 level 2. It's not true for U1 level k. It's only an accident for U1 level 2 because there is one anyon of spin a quarter, and the spin a quarter and minus a quarter is the same, mod a half. It's not true for U1 level k. So the conjecture here is that when the mass is exactly 0, the theory... Pure Chern-Simons. Okay, so let me explain this point a little bit more. So if you look at U1 level k, it has anyons with the following spins. 1 over 2k, 4 over 2k, 9 over 2k, and so on, until you get to k squared over 2k, which is a half. So until you get to a half. If you compare that with U1 level minus k, there are anyons of a spin essentially minus 1 over 2k, minus 4 over 2k, and so on, until you get to minus a half. Right? But the spins are defined mod a half, because a half is the spin of a local operator. So we cannot measure the spins in Chern-Simons theory exactly. We can only measure the spins mod a half, because we can always trace the line with the local operator of spin a half. So what you have to ask is whether to see if U1 level k and U1 minus level k is the same TQFT, you have to ask if this set of numbers is the same as this set of numbers mod a half. This is not true for generic k. For generic k, there is no object here which has that spin mod a half. It's an accident for k equals 2 that these two sets are the same mod a half. So it's an accident for k equals 2 that U1 level 2 and U1 level minus 2 is the same. So classically, these two Chern-Simons theories are not the same.
No, I was saying something much more elementary. I was saying that conjugation would relate.
No, but that's true for any of those two sets. But there is something else that happens for U1 level 2, that it's an automorphism. It's an automorphism of the set of lines.
I mean, we don't have to listen to U1 level minus k that line with U1 level k.
Right. They're always related by reversal of orientation, but the magic that for U1 level 2 is that reversal of orientation is an automorphism of the fusion algebra. And it's an accident. And these accidents are kind of so there are several such accidents in the world of Chern-Simons. Nobody has classified them. But this is not the only example. There are several Chern-Simons matter theories, pure Chern-Simons theories, which have this accident. Okay? So this accident is very important because at 0 mass, one can now, because it's U1 level 2 here and U1 level 2 here, we can sort of factor it out. So the idea is that at 0 mass, where the theory is strongly coupled, the theory flows to U1 level 2, tensored with a free fermion. This is just a free complex fermion, not coupled to anything. So this is a free complex, a free Dirac fermion. Not charged under anything.
This you're just saying.
Yes, I'm not deriving it. I'm just saying that this is an example where you can see how anomaly matching nicely works. So we have a one-form symmetry in the ultraviolet with anomaly 1 mod 2. At the massless point, it's saturated by a pure Chern-Simons TQFT. There is another example with a non-abelian group that arises in the context of supersymmetry, such as, I mean, this is another example where there is a little bit of supersymmetry. So we can discuss n equals 2 supersymmetric 3D model of SU2 gauge theory coupled to a chiral superfield. In the chiral superfield in the adjoint representation. Chiral superfield in the adjoint representation. This is another example where the charge lattice is not populated because we don't have a fundamental particle. So this is another example where there is a Z2 one-form symmetry. Okay, so people have checked with partition function techniques that this model seems very similar to just a free chiral superfield Y, which is not coupled to any gauge theory. But a small observation is that this doesn't match the anomaly because there is a one-form symmetry here. And using that formula, you can check that the anomaly is 1 mod 2. But there is no one-form symmetry that can act here because it's just a free chiral superfield. So in fact, the answer is this. There is another U1 level 2 here, which matches the Z2 one-form anomaly. And you can check that using the S3 partition function. So you can actually see that using the S3 partition function. So that's another example where you can use of a nice anomaly matching, which is a little bit reminiscent of this. It's kind of similar. So this is how one-form symmetries arise in Chern-Simons matter theories. The idea is that Chern-Simons theories can carry some one-form symmetry, some one-form anomaly, and that leads to various constraints on the infrared. Okay, now 4 dimensions. Are there any questions about 3D examples? Oh, I wanted to mention one additional thing about bosonization. I wanted to mention why one-form symmetries are omnipresent when you study examples of bosonization. So when we study bosonization in any dimension above 2, one-form symmetries are going to be everywhere. They're going to be ubiquitous because of the following fact. Suppose you have a bosonic theory on one side and a fermionic theory on the other side. Now, the partition functions of fermionic theories depend on the choice of a spin structure. Here you need to choose a spin structure. While the partition functions of bosonic theories don't know about any spin structure, they don't care. So how can it be possibly true that such theories would be the same if one depends on the choice of spin structure and one doesn't? So the idea is that the spin structure choice is like a one form because it's in the spin structure choice has to do with H1 with coefficients in Z2. So it's a one form.
So it changes spin structure as
well.
Changes spin structure as H1.
Right. You assume that there is a spin structure. So there's no obstruction.
But there's no canonical basis on the left side for that. There's no canonical spin structure.
Right. So the space of spin structures.
So that means that the answer on the right side does depend on that choice.
Right. Well, the left-hand side does not. So how can these two theories be dual?
I appreciate the question, but I'm saying it's not just H1 and H2. That's what I'm saying.
Why not?
Difference of two spin structures is that, but not a given one.
I agree. H1 in Z2 is like the deformation theory for spin structure.
H1 Z2 torsion, H1 Z2 act.
Is an act, exactly.
Yes.
That's what I'm saying.
Yes.
There's no canonical basis.
Right. So I'm just running.
The difference between two.
Not having canonical, how does that feature in the discussion? It should be some.
There is no canonical choice. I agree with that. But the space of this is the space of deformations of spin structure. So the way these bosonization dualities work is that the spin structure on this is conjugated like Fourier. So this is like a one form. You can introduce a certain d minus 1 form or a 2 form. In 3 dimensions, it would be a 2 form here. So the idea is that you can couple the bosonic side naturally to a 2 form gauge field. And then you can interpret it as a gauge field for a one-form symmetry. So one-form symmetry on bosonic side by Fourier transform can be related to a spin structure on the right-hand side. And that's how the bosonization works in higher dimensions. That's the whole trick. That you need the one-form symmetry in this theory, and then you can reproduce the dependence on the spin structure on this theory. I agree that there is no canonical choice, but there is the space of deformations is the same.
So do you have an example where one-form symmetry is not manifest in the ultraviolet, but emergence in the infrared?
Accidental symmetry, you mean? Yes, there are many examples where one-form symmetry is an accidental symmetry. Do you want to see an example, just for the heck of it, or what?
Well, like global, like ordinary global symmetry of just one dimension.
Yes, you can. One-form symmetries can have anomalies. They can be spontaneously broken. They can be accidental. I can show you an example for the heck of it if you're interested. Yeah? Okay, so I mean, you can have a stupid example. I can show you a stupid example for an accidental one-form symmetry. So just take U1 level 0 plus charge 1, sorry, U1 level 1/2 plus charge 1 fermion. Okay, this is a very famous theory. I'll tell you what it's dual to. So here there is no one-form symmetry because there is a charge 1 fermion, so the lattice of charges is populated completely. Okay? Now people have studied the dynamics of this theory as a function of the fermion mass. If the fermion is extremely heavy, we integrate it out, the level is shifted by 1/2, we get U1 level 1. And here we get U1 level 0. Now this U1 level 0 is like the deep infrared theory. So there is an accidental one-form symmetry because there are no charged particles. Okay, so it's just a compact boson. And a compact boson is the same as a free Maxwell field in 2 + 1 dimensions. This is the same as a compact boson, phi, which is valued in S1. So this theory has an accidental one-form symmetry, which is isomorphic to U1. But of course, the ultraviolet theory did not have any such symmetry. And this is violated by the Polyakov mechanism if you added monopoles. You could add monopoles. This would lead to some mass, and it would break the shift symmetry. So you could violate it under some, well, no, sorry. Let me just say it correctly. So this theory has no one-form symmetry, but in the way I've phrased it here, this would have an accidental U1 form symmetry. So there is a compact boson here, and this Chern-Simons TQFT turns out to be trivial. If you look at the space of lines or the spins that were somewhere here before, there is no non-trivial anion. So this is a trivial TQFT. And in fact, because of the fact that there is a circle of vacua here and no vacua here, people have conjectured that this is dual to the XY02 Wilson-Fisher model. So this is a Wilson-Fisher-Landau-Ginzburg type transition. So this is a stupid example with an accidental one-form symmetry. But I can give you lots of... I said something wrong. The shift symmetry here has to do with the monopole symmetry here. It's a zero-form symmetry. In addition, the compact scalar model has a one-form symmetry that is given by the following conserved charge. It's a two-form current, so it's conserved, and it's conserved, so it leads to a topological line operator in the compact scalar theory. And this one is unbreakable, and it's an accidental one-form symmetry in the infrared. If you included charged particles, monopoles, so to speak, then it would be broken. But as it is, it's unbroken. Okay, so it's not easy to break the symmetry at the level of effective field theory. It's an accidental symmetry.
So that symmetry cares about how the lines wind around the target S1?
So you can define a line. So this in 3 dimensions, one-form symmetries are generated by topological lines. How do you define the line? You just say that around that line, phi picks up 2 pi. Yes. So it's defined like a 't Hooft line. And you can prove that this line is topological in the theory of a compact scalar. And it's not easy to break it at the level of effective field theory, this topological symmetry.
Winding vertex operator leads to
Yes, it's like a winding vertex operator in 1 + 1D. It leads to this one-form symmetry. So this is an example of a one-form symmetry in the infrared that is hard to break. Okay, so now I just want to... I'm basically out of time, right? So we won't discuss 4 dimensions. Maybe just if there are some questions, I can answer some questions. Oh, yeah, it's kind of pointless. I've been rushing through 3D and 2D. I can rush through 4D. If there are any questions about the subject. Yeah.
Can you give a 4-dimensional example?
Super Young-Mills is perhaps the nicest example. N equals 1 pure super Young-Mills. This is a system of a gauge field with a fermion. In the adjoint representation, therefore, it has a Zn one-form symmetry. Yeah, and you can ask, what is it good for?
How about spin? Let's take the gauge group to be the orthogonal group.
So this is SUN.
Let's not talk about that.
What do you want to do now?
Let's take orthogonal group or symplectic group.
Okay. So actually, I'll say a few words. Yeah, I'll just say a few words. Let's just discuss SON for a second. Maybe I'll just make one comment about 4D. So in the examples we've seen so far, the one-form symmetry arose from the center of the group. Now, for even n, the center of SON is Z2. So you might think, suppose we studied SON gauge theory with an adjoint fermion, we will have a Z2 one-form symmetry. Great, right? But it turns out that it's actually Z2 times Z2. This times in quotation marks. Well, it's Z2 times Z2. Because there is one that is manifest due to the center of the group, but there is also one that is magnetic. So in 4 dimensions, the novelty is that sometimes one-form symmetries cannot be seen from, with your naked eyes. You have to look. There are also magnetic one-form symmetries. Essentially, that's because this is a two-form and this is a two-form, and they can be both conserved. So they can both lead to a one-form symmetry. This is a novelty in 4 dimensions. And this is very important because these magnetic one-form symmetries can also have 't Hooft anomalies. And there is a lot of constraints on the infrared dynamics of gauge theories due to that stuff. So this is one thing to say. More generally, if you studied SUN would have just an electric one-form symmetry. I mean, the obvious one, super Yang-Mills. But if you study the quotient, you could also get a ZQ instead of the Zn. So you'll get something like this maybe, but it could be more complicated. This is just a very naive answer. It could be more complicated. So this is one thing that's new about 4 dimensions, and you can look it up in the literature. This plays an important role in the dynamics of 4-dimensional gauge theories. But, I won't have time to explain it systematically. So there was somebody else before. Yeah, Sergey, and then yeah.
You mostly talked about, except for anomalies, you talked about this as global symmetries.
Right.
When we try to gauge one-form symmetries, would you say non-abelian BF theory, saying 4 dimension is not well defined?
Say again?
So trace H, HB, where both are the algebra values.
You're asking if there could be a non-abelian one-form symmetry?
Yeah, as a gauge symmetry.
Well, as a global symmetry, I think that there cannot be a non-abelian one-form symmetry. You can have a two-group. A two-group is also very complicated. A two-group means that the zero-form symmetries are not well-defined by themselves. But I'm not aware of how to construct non-abelian one-form symmetries. Are you aware of how to do that?
So probably your definitions will be modified. Because with your definition, they are...
Yeah, with my definition, they have to be abelian. I just don't know.
Two-form symmetries?
I mean, I studied lots of dynamics of gauge theories in the recent year and a half or two, and I've never encountered something like that. Maybe just because the way I'm using it cannot allow for non-abelian symmetry, but I mean, these magnetic symmetries are very important in the dynamics. So maybe what I'm trying to say is that even the abelian stuff is already constraining and interesting, and not very well explored yet. For example, in this system, people don't know the 't Hooft anomalies yet. I know the 't Hooft anomalies for the obvious one, but there could be mixed 't Hooft anomalies, and I don't think anybody worked them out for the Z2 times Z2. You need, I mean, there are 4 different cup products you can write down. There is B wedge B prime, B wedge B, B prime wedge B prime, and I don't think anybody worked it out. This could be interesting for the dynamics of SON. Yeah. Yeah, you can have two-form symmetries that could correspond to codimension 3 topological surfaces. I don't know what to do. I mean, I don't know if they arise in any natural fashion, so I wouldn't be able to say much. They could arise in some. I just don't know if they arise naturally.
You mean like 5 and 60 theories which have strings?
Yeah.
That's very natural. You expect that now.
Yes, indeed. Yeah. There was another question here. Yes.
So you paused when you were talking about the product structure. Is there some sort of action of the magnetic symmetry on the electrostatic symmetry or something like that?
So you could say in some sense, yeah, because if there are mixed anomalies, that means that the intersection of an anomaly basic, okay, maybe I should say something trivial, but let's do, for example, 1 + 1 dimensions, 1 + 1, and let's just talk about zero form symmetries, ordinary orbifold-like symmetries. So suppose you have a 1 + 1 dimensional system with Z2 times Z2 symmetry. That can have a 't Hooft anomaly. So there is a possibility for a discrete 't Hooft anomaly in 1 + 1 dimensions if the zero form symmetry is Z2 times Z2. And you can ask, okay, how do I diagnose it? And the answer has to do with what happens when two topological lines intersect. So you have a Z2 topological line and another Z2 topological line. And the algebra, if they act like this on some local operators, the algebra is Z2 times Z2 because there is no other group with 4 elements. But if they intersect like this, you can have funny contact terms. And the contact term is like ±1, and that has something to do with the anomaly, the 't Hooft anomaly. So likewise, for higher form symmetries, like 1 form symmetries in 4 dimensions, the algebra is going to be Z2 times Z2 when you act on the K strings, on the stable strings of the theory. But when they intersect, you can get various phases which would capture the 't Hooft anomalies. So, yeah.
If you spontaneously break a global one-form symmetry, do you get anything like Goldstone bosons or anything like that that arise?
Right. So if you spontaneously break a global one-form symmetry, if it's discrete, then you get deconfinement. So I'm just gonna write what is. So suppose we spontaneous break a one-form symmetry. So generically, what you get is deconfinement. What does it mean? It means that some Wilson lines have perimeter law. On some strings some strings are deconfined that they don't want to look like flux tubes. They may want to spread around. That's what it means to generically break a discrete one-form symmetry. But if it's continuous and you're in 2 + 1D, if it's a U1, you can say more, because then you can think about it as F mu nu, as a conserved 2 form, continuous conserved 2 form, and acting with it on the vacuum, you get a massless photon. So you can think about the massless photon as a Goldstone boson of a one-form symmetry. It's a special case of deconfinement, the massless photon. So in some sense, the photon can be viewed as a Goldstone boson of a one-form symmetry.
Any other questions? I have one quick question. So you mentioned that the zero-form symmetries you were considering, or most people consider, are these group-like structure, but people have extended to non-group-like structure.
Yeah.
How about the one-form versions? Are there any hints that they exist and higher forms or versions of those?
Yeah, in principle, you could have 3 groups. There could be examples where when you study what happens to the one-form symmetries, you might get 2-form symmetries when they intersect. So in principle, there could even be 3-group symmetries. Yeah, I don't know if there are interesting examples of those. That's the main issue. I just don't know if it's interesting for something. But in principle, it could exist. Two-group symmetries definitely arise in very interesting examples with non-trivial dynamics.
Any other questions?
So very naively, the one-form symmetry is the symmetry which is generated by one form. The generator is a one form, and the parameter of transformation.
Exactly. Yes.
So, but that's like a gauge field, one form, right? But what about the symmetries where when the parameter is like a vector field, like diffeomorphisms? Can we have some theories for those?
Well, when global symmetries, zero-form global symmetries are generated by constant zero forms. Global one-form symmetries are generated by constant one forms. A constant one form is like a flat gauge field. If you gauge them, then you need to also add a dynamical 2-form. You need to add the classical 2-form gauge field so that the whole action is invariant.
Yes, but we know that if we want to gauge diffeomorphisms, I gauge them not by a 2-form but by a metric.
Correct. So because that's right, because the transformation.
Like a translation?
Right. Yeah, but here I'm talking about transformation rules of, you have various fields, let's say a gauge field, and it transforms to gauge field plus a flat connection, that's a one-form global symmetry. That's what we call a one-form global symmetry. Now, and this can be gauged by coupling it to a two-form gauge field. Now, it could be that you can also come up with examples where you need a symmetric two-form, like gravity or something. Yeah, I don't know if this is relevant for something.
I don't know. And one way you can think about this is that you're not changing the type of symmetry. You're changing the generators, right? So you can think of the
The question was gauging space-time symmetry.
yeah, but you can think of it as replacing T by D, by the derivative.
I don't know. One-form symmetry in Lagrangian examples arises by taking the gauge field and shifting it by flat connection. This cannot be removed by an ordinary gauge transformation because it's a flat connection that has non-trivial holonomies, which are not valued in 2 pi. So this is what a one-form symmetry is. And this is a symmetry of the action only if there are no charged particles under the corresponding subgroup that the flat connection generates. This is how it acts on the Lagrangian.
Okay, if there are no more questions, let's thank Zohar again. Thank you very much.